Hello, everyone. It's my honor to present my topic regarding microwave heating of packed-bagged reactor. I'm Fang Lin, currently an assistant professor in the Department of Chemical Engineering at University of Massachusetts Lowell. My group is currently built. I have two PhD students, Mingyu, who is in charge of the CO2 electric reduction project, Daniel, who is in charge of the microwave catalysis project. I have two undergrad students working with me, James in the machine learning. Emily is in charge of the light activation project. We acknowledge the computational resources from ICIT, CERTA at Argonne National Lab, and I'm GHPCC at Boston. And if you are interested in the research-wise of my group, and we are currently recruiting the PhD students as well as the postdoc. So if you are interested, feel free to contact me after the presentation. Before giving a detailed presentation regarding the microwave catalysis, we want to introduce what is the overview of the multi-scale simulations. That is what currently my group is doing. So we care about the atomic phytosecond until reactor scale second, this multi-scale modeling and multi-physics involved inside this modeling work. For the atomic scale, we mainly use quantum mechanics method to approximate by density functional theory, trying to look at what is the interactions between the reactants and the surface. We can scale up to molecular level, trying to see what is the real catalyst look under certain temperature, pressure, or concentration of the proton or pH. We can even scale up to micro scale, mainly use mean field microchem model, and we can see directly quantitatively comparison between the experiment and the theory. What is the yield? What is the selectivity of certain reactions? We can go up to continuous transport models, trying to see what is the mass transfer, heat transfer approximate by the finite element method. And this is extremely important when your reactions is non-uniform temperature or non-uniform pH in the electrochemical cell. So this is an overview of the multi-scale simulation. Then back to our main presentation regarding the microwave heating of packed bed reactor. We will talk about the hotspot formation under the microwave reactor. We will talk about how this hotspot formation can be treated numerically inside the microwave reactor, as well as how this hotspot formation can assist hard to react reactions such as methane steam reforming reaction. Start with the background. We know that the renewable energy driving the electricity is continue dropping the price. But the challenge of this renewable energy driving the electricity is hard. It's very expensive to storage. Well, to solve this storage issue regarding the renewable energy, we can use renewable electricity to activate the microwave radiation, and we can activate hard to react molecules such as methane to generate valuable products such as ethylene from methane coupling. And if you can have 70% of the electrical to chemical power conversion efficiency, you can reach a profit of $20 billion in the USA and Canada. Using microwave, it has its own advantage, such as rapid heating, such as preference heating of the material. It can improve the energy efficiency. So if you microwave heating on a microwave high absorbability material, it can be rapid heating, can improve the energy efficiency. At the same time, if you are investigating, for example, gas solid reactions, your solids can be preferred to heating by the microwave, and your gas phase will be cold because it couldn't absorb microwave, and it will eliminates the side reactions happen in the gas phase. So we want to investigate using this advantage of microwave technology to do the gas-solid heterogeneous catalytic system. It also have the concern because it's really hard to understand the microwave radiation heatings combined with the chemical kinetics because the mechanism of the microwave heating is still lacking. So it's hard to design efficiently how to use energy from the microwave to transfer efficiently to the chemicals. And it's really hard to scale up for the microwave reactor as well. So in our presentation, what we trying to do is trying to understand the role of the microwave heating in microwave assisted gas solid heterogeneous radiation reactions from a theoretical point of view. So if we can understand well, then we can better design this microwave reactor. One of the interesting things in the microwave technology is that you can see there is a hot spot forming in this connecting grips inside the microwave. So there, if you have particles contacting each other, and if this particle has really high microwave absorbability, it can form this intense hotspot. Well, if this hotspot is nearby a rich environment of the sodium and the potassium, it will lead to the plasma. So microwave plasma is also one of the hot topics in the recent decades, trying to use microwave plasma to efficiently converting hard react molecules to valuable chemicals. And this hotspot can also use for the heterogeneous catalysis, for example, catalyzing the propanol to acetone over iron oxide at 200 degrees Celsius. What they found is under microwave heating, the yield of acetone is significantly enhanced as compared to the conventional heating. And when you have this hot spot formation inside this iron oxide, that may be the reason leads to that high enhancement of the yield of acetone. So what we are trying to investigate in this project is what is the dedicated factors to lead the hot spot formation under the microwave heating, and how this hot spot can enhance the kinetics of heterogeneous catalysis. And is there any numerical treatments can treat this hot spot formation inside the microwave reactor? The computational method we use in this research is the multi-physics inside the console, approximate by the finite element method. And we are simulating 5 particles contacting each other to represent the packed-back reactor. And we have the microwave input from the top layer to the bottom layer. This is a periodic setup so that you can imagine infinitely size of the X and Y direction of the packed-back reactor. We are trying to use the finite element method to solve time harmonic electromagnetic wave, which is mainly conducted by the electric field and magnetic field. We are trying to solve the heat transfer inside the microwave reactor, mainly is the convection and the conduction of the heat transfer. The heat source is from the electric field mainly. We also will solve the velocity field, the mass transfer, as well as the reaction kinetics. And the reaction kinetics is taking an example of mass and steam reforming reaction. Okay, then the next part we will tell about the result about the hot spot formation. What kind of the factor can lead the hot spot formation? We did by simple example case, which is the iron oxide, because we know the dielectric constants, the material properties of iron oxide. We found that with the iron oxide, it can form this hot spot, and as you increase the time, it can be constant 200 degrees Celsius difference between the hot spot and the rest area of the catalyst particles. It reached the hot spot at the beginning at 20 seconds after heating. and that is the maximum temperature difference between the hotspot and the rest area of the catalyst particles. And you can imagine if you catalyst pipe bed has this hotspot formations, it may lead to a better convergence because this hot temperature with short residence time as compared to the conventional heating. Then the next part we want to know is what is the factor can lead this hotspot formation. So we tested different parameters such as microwave frequencies, microwave power, the heating time of the microwave, and the materials you are heating, such as the dielectric constant, such as the thermal conductivity, the density, the heat capacity. And we are with the questions, which parameter can dedicate the hotspot formation. We did the principal component analysis using all the data we generate from console multiphysics. And from PCA, you know the PC1 should be the most important dominant factor to dedicate the hotspot formation. So we further zoom in to our PC1. What is our PC1? Well, we found that when you have the effective thermal diffusivity, that is the dominant factor, which is related to the heat capacity, the thermal conductivity, and the density of the material. And we also found another important factor, which is the dielectric constant of the iron oxide. So we got our current conclusion regarding the hotspot formation is that we need effective thermal diffusivity will be one of the dominant factor to lead the hotspot formation, as well as this particle needs to be have microwave absorbability. Then with this conclusion, we try more materials for the iron oxide, for the hotspot formation, including the material iron oxide, the activate carbon, the perovskite, and silicon carbide. What we found that is when a material with high microwave absorbability and low thermal conductivity, then that material can lead to a significant hotspot. But when you have really high thermal conductivity, even though your microwave absorbability is high, then this hotspot won't form, because as long as this hotspot form, it will distribute the temperature to the rest area of your catalyst. So the silicon carbide doesn't have hotspot formation. Then the next part we want to know is that what is this hotspot role in the heterogeneous catalysis, mainly the gas-solid heterogeneous catalysis? We use a study case, which is the methane steam reforming reactions. Why we use this case? Because hydrogen, 95% of the hydrogen from the United States is generated from this methane steam reforming reaction, and the hydrogen can be used for the ammonia synthesis for agriculture. The syngas generated from methane steam reforming reaction can directly input into Fischer-Tropsch reaction to generate long-chain hydrocarbons. And this reaction itself is very important because it has broad application in the States. And there are also challenges of the methane steam reforming reactions and the conventional heating. Because this high temperature requirement, the methane steam reforming reaction always have low energy efficiencies in the industry application. And also because of this high temperature requirements inside the methane steam reforming reaction, if you have the conventional heating, everything is heated uniformly, then you will have very high temperature of the gas phase that will lead to the side reaction, which is the coke formation for the methane steam reforming reaction. And after you form this coke formation, it will deactivate your catalyst. Then the stability of this reaction is also not good in the industrial application. We want to use microwave technology to enhance this methane steam reforming reaction. So we have our catalyst at the core and at shell. The core will be some good performance of the microwave absorbability material. Then it will heat rapidly in the microwave and selectively, so that it will solve the challenge of the high temperature requirements of methane steam reforming reaction, as well as improve the energy efficiency because it heats rapidly, it heats preferably for those materials you want to heat up. And it won't heat the gas phase, so that your gas phase will keep cold, then you will eliminate the side reactions raised by the side gas phase reactions. Then that will solve the Meson steam reforming challenge, which is listed here. Then let's do some analysis for comparison between the conventional heating and the microwave heating. First we did is the energy balance for the Meson steam reforming reactions. We have our catalyst represented by these 5 particles in this contacted to each other and in these reactors. We have our hot gas is from the top and generate input from the hot to the bottom. We calculate what is the temperature required for the hot gas to reach the equilibrium. And we compare with our full computational fluid dynamics simulation in console multiphysics. We found its majority agree with our analytical calculations, just a slight difference. And this difference can be because the residence time of this catalyst bed is not long enough to fully finish this Meson steam reforming reactions in this reactor. And we did a similar analysis for the microwave heating. We calculate the energy balance, what kind of the power input can happen this Meson steam reforming reactions. And we found that as we analytically solve this microwave heating at certain equilibrium converging, that is the power input for each flow rate. And we also calculate at certain flow rate, which is this point, the computational fluid dynamics gave us so low Meson convergence as compared to the analytical simulations. And that is because majority of the microwave didn't absorb by our catalyst bed because of the current geometry setup. Only 31% of the microwave was absorbed by the particles. So this gave us the hint that we need to design our microwave reactor, design our microwave packed back particles so that it can fully absorb the microwave power so that it can reach even higher equilibrium as compared to the conventional heating. And we further tune the flow rate, basically tune the residence time of the microwave reactor as well as the conventional heating. What we found that as we increase the flow rate for the microwave heating, the Meson conversion is actually increased. That is so different as what we expect for the kinetics, because as we increase the flow rate, the residence time is decreasing. Then your Meson conversion should be decreased. So from this result, we have our preliminary conclusion is that with a higher flow rate and shorter residence time, the microwave heating can potentially reach higher conclusion as compared to the conventional heating case. So this gives us a hint that when we design our microwave reactor, maybe we can have a shorter bed and have a better energy efficiency as compared to the conventional heating. Then go to the last part. When you have the contact particles inside your reactors, it's really hard to mesh out for your simulations. The mesh will give you really hard time to converge. So there are some numerical treatment for the contacting part in the packed bed reactor under the conventional heating. They add the bridge, the researchers add the bridge, and they found that when you bridge dimensions or the particle dimensions is around 0.1. The bridge method can treat the contacting particles, the converging issues. The same time, it will give similar accuracies as compared to just having the particles touching each other. And similarly, when the particles are touching each other, it gave us the hard time for converging in the microwave reactor as well. Can we use the same treatment, the bridge treatment, to treat the intraparticle contact for our microwave reactor? So we did a similar thing just for the heat transfer. We found that with different bridge sites, it will change our temperature profile for the intraparticle contact. You can see that as the bridge size increase, the temperature of the hot spot as compared to the rest area of the catalyst bed are significantly changed. And the the kinetics, we use A to B artificial kinetics, and we found that with the bridge treatment, we also alter the kinetics of A to B convergence as well. So we need to think a better way for this numerical treatment of the bridge, how we can leverage out about this bridge material so that we won't change the temperature profile at the same time we won't change the kinetics of the reactions under the microwave heating. Going to the conclusion that we know the main factors leading the hot spot formation is the microwave absorbability as well as the thermal diffusivity. And we know that we need a better way to numerically treat the bridge. For example, how to tune the materials of the bridge, how to tune the size of the bridge, and how we treat the catalytic surface area of the bridge so that we can keep the same temperature profile, the same kinetics as we use bridge treatment for the touching particles. And we also have the pre-conclusion that with higher flow rate and shorter residence time, the microwave can reach higher convergence than the conventional heating case. So currently our group is mainly focusing on heterogeneous catalysis, including electrocatalysis, microwave catalysis, as well as the thermal field effect, field-induced heterogeneous catalysis using multi-scale simulations. If you are interested in this perspective of the research, feel free to contact me. Thank you.